I'll introduce Dr. Sean Yu from MTS Systems. For those of you that know Sean, you've probably worked with him, you've seen him. Sean is one of our knowledge experts in hybrid testing, and he covers all aspects, whether it's civil engineering or ground vehicle. He's extending some of the testing methodologies into wind testing and some of our aerospace applications as well. Sean, I think you've installed probably over 100 hybrid systems worldwide, those being in China. So, you know, if you have any technical questions, Sean's really one of our experts that really can help guide you and direct you on hybrid testing. So I'm going to turn it over to Sean and let him have the presentation. Thank you.
Thank you, Ray. Yeah. And yeah, today I'm going to talk about hybrid simulation in civil structure. I will cover MTS hybrid simulation solutions and give you an example of what hybrid simulation is and the future trend and conclusion. So, like Shirley just mentioned, you know, in civil structure testing, earthquake simulation, so they are mainly three types of testing. One type is shaker table test, and you can build a shaker table like this, and you can build your specimen and put it on top of the shaker table, and then you can simulate ground motion. And if you have an iterative approach, the ground motion can be simulated really accurate. It's a dynamic testing, so the accuracy is the advantage for this kind of testing. However, like Shirley mentioned, even for the biggest shaker table in the world, it's difficult to do full-scale testing. You know, if you have a long span bridge and if you have a really tall building, there's no way you can test it in full scale. And then you have to shrink down the specimen. And for example, Tongji University did a shaker table test on Shanghai Tower. It is a very tall building, so they have to shrink down the specimen to 1:50 scale. So then the accuracy is a question, and most of the people do not believe the result of that shaker table test because you shrink down the specimen so much. So another type of testing is the substructure pseudostatic test. And you test a substructure, and you load it really slow, and with sine wave or a triangular wave, and to find out when the structure fracture damage. So this kind of a substructure, slow kind of test is very cost effective. So you only test a substructure. So specimen is not expensive, and you have your slow actuators and some fixture, simple fixture. So yeah, it's a very it doesn't take as much to do this kind of test. But the disadvantage is the loading is not realistic. So you use three cycles of sine wave, and then change to another level, another 3 cycles of sine wave or triangular wave. So no earthquake is like that. And so the loading is not realistic. Yeah. So that's the disadvantage of this kind of test. So another type of testing is hybrid simulation. So it breaks the structure into two substructures. So one is a numerical substructure simulating the overall ground motion, simulating the loading on this physical substructure. So the numerical substructure calculates the input for this physical substructure and send the command to the lab, and controller gets the command and push the substructure, and then measure the response and send back to the numerical substructure, and the numerical substructure calculating the next movement. What's the new command? So repeating that. So this is a hybrid simulation. So the advantage of this is it models a dynamic event, earthquake or whatever. So the loading is more accurate than the pseudo-static substructure testing. You can simulate, whatever kind of earthquake. So it could be El Centro or other kind. You can do a lot of things on loading. So the dynamic loading is more accurate. And on the other hand, so for the hard-to-model substructure, it could buckle, it could fracture, so the model cannot capture the nonlinear property. You can put it into the lab, and then the lab does the real loading on this piece, and it measures to the nonlinear region, and so the test is more accurate in that sense. So because of that, the model is more accurate because the hard-to-model portion is in the lab testing. So yeah, the model is more accurate, and the test is more accurate because the loading is from the dynamic analysis. So because of these advantages, so a lot of researchers start to use this method to study the earthquake and other kind of events. So MTS has been in this field for many years, and in the early days, MTS developed our own hybrid simulation software. At that time, we called it pseudo dynamic software, developed by Benson Schenk of Colorado University. Now he's in San Diego, and that's early days. And around the year of 2000, and UC Berkeley developed OpenFresco software tailored for hybrid simulation. So then we worked closely with UC Berkeley to implement that approach. So now we have our hybrid simulation solution, and we have a real-time low hybrid simulation and soft real-time hybrid simulation solutions. And we offer those solutions to our customers. And so not only in civil structure, but also in ground vehicle. So now we try to move hybrid energy to aerospace. So currently, we have more than 110 customers, in hybrid simulation customers, in ground, mostly in civil structure, and some in ground vehicle, and one in wind energy, and hopefully, one in aerospace. Hopefully, we will grow our list, and that's definitely the trend. So, as I said, MTS offers different kind of hybrid simulation solutions. if you have a structure like a concrete, like a steel, it is not rate dependent, and the lab can only can provide the stiffness term, and then the damping term and the inertial term can be all provided by analysis model. So in this case, the test could be very slow. Then you can save a lot of money. You don't need to use fast actuators, and you don't need to do real-time hybrid simulation and those a lot of compensation, stability issues, stuff like that. So you don't need to deal with. So it's much easier and lower investment. So we have our slow hybrid simulation solution to offer. So in this solution, and you can have analysis PC, and analysis software is running here, and then analysis software generates command. The command can be sent through OpenFresco, so that's the UC Berkeley software, and the OpenFresco sends the command to our computer simulation interface software, so that's MCAS software. So that software sends the command to our controller, and then the controller executes the command and get the feedback. So the feedback go back same way to the computer model, and then it calculates the next command and goes the same way. So in this solution, so the key part is UC Berkeley's software called OpenFresco. It handles the communication. It sends the command from analysis software, such as OpenSys, and to our software called computer simulation interface. And so on one side, you have an analysis model, maybe OpenSys model or ANSYS model or whatever the model. And then, so the command is sent to the box here is called OpenFresco. It has different modules, and transfer the command into different size, into different coordinates, and then sent to our software called the computer simulation interface. So in this software, we map the OpenFresco signal to different control channels of our controller, and in different orders, in different units, and then OpenFresco needs feedback. So in certain order, and then our computer simulation interface software, sends the feedback signal in certain order and go back to OpenFresco, go back to analysis model. So, and so OpenFresco is the middleware connect to the analysis software here. So the analysis software can be multiple kinds. It can be ANSYS, can be OpenSys, can be MATLAB, Simulink, and Adams, and as long as the software has a user-defined element, then we can use this kind of software, use OpenFresco, and use DSI and do the hybrid simulation. So that's the software part. Hardware, and you can simply use our controller and use our actuator, and the actuator could be fast, could be slow. It doesn't matter because this is a slow hybrid simulation. So whatever the hardware you have already probably is good enough to do this kind of quasi-static hybrid simulation. So the only piece you need is this computer simulation interface software. OpenFresco part is a free software because It is founded by NIST, and it's open software you can download, we can provide, we can install. Yeah. So this kind of quasi-static hybrid simulation solution is really, really cheap. So really convenient for you to implement, yeah, as long as your specimen is rate independent. However, in many cases, your specimen is not rate independent, it's rate dependent. For example, you have a tall building, you have a mid-level isolation, so you are simulating earthquake here. So the response of this structure is very dependent upon the rate. And the earthquake got to be real time. And the earth, so the test got to be real time, same scale like the earthquake. Otherwise, the inertial term will not be right. And then the response of the structure is not be right. So then, in this kind of case, the hybrid simulation got to be real time. And so the experimental part got to provide the inertial part and the damping part and the stiffness part. So the test got to be fast, the hydraulics got to be fast, the simulation got to be fast. So in this kind of a real-time hybrid simulation, MTS offers our solution. So in here, you got to build your analysis model, and in terms of Simulink, and because Simulink model can be converted to C++ code, and this C++ code can be downloaded to a special PC called Target PC. So the model is created in Simulink environment and downloaded to a Target PC. So this Target PC has a very, very simple operating system. It's not like Windows and stuff like that. So the overhead is really low. And it only solves the equation written in forms of C++ code. So it solves really fast. And then the command is stored in a SQUAMNet card. So its writing is really fast, not like hard drive or anything like that. So the storing is really fast, and then the command from this SQUAMNet card is transferred to the controller right through fiber optic cable. So the data is transferred very fast. And in this controller, our controller, inside there's another SQUAMNet card, and got stored in here really fast. And then with the fast controller, fast actuator, hopefully the real-time requirement can be met. So you got to be really fast in solving, got to be really fast in storing, transferring, and then execution. Yeah, everything has to be fast. Then you have a chance to catch the real-time requirement. Even so, your model cannot be very complicated. Yeah. So hardware-wise, you can have our controller, but you need to add a SQUAMNet card inside. Then we have a special software you need to install here so that a SQUAMNet card command can be executed using our servo valve and actuator. Yeah. So you have to do some upgrade, install new software, and install SQUAMNet. So that's in our controller. And also, the actuators got to be faster, bigger servo valve, that's for sure. And the disadvantage of this approach, like I said, you got to build your model in Simulink. a lot of times that's difficult because, if you want to build a FEA model, a many degree of freedom, it's very difficult to do, to build your model in Simulink. So then we have our soft real-time solution. So in this case, and the analysis model software can be non-real-time software, like OpenSys. It runs in Windows environment, and it doesn't know what's the real time, so that's fine. And as long as the model can be solved fast. Yeah. So the command, after solving the command is sent to OpenFresco again, but to a target PC. To a target PC, this is acting like a real-time controller, acting like a coordinator. So this target PC has a special program running called a predictor corrector. So it's acting like a coordinator. It looks at the real time, and it watch for the simulation as well. So this piece of software is the. So this is the predictor corrector in the middle. In one side is the real-time test system with our controller. Closed loop rate is about 1,000 per second. And on the other side, there's this non-real-time analysis model, and it runs in its own step size. It's not the closed loop rate. So maybe the closed loop rate is here, the little dashed line representing the closed loop rate, but a non-real-time analysis model running not that closed loop rate, but it's a larger step size. So the model can be more complicated because the step size is longer. So in between, this predictor corrector model is running, so it keeps the real time, and then for each moment, each closed loop rate moment, each clip, and the test need a command, so it watch for the analysis model. If the analysis model at this moment is not solved, and then it predicts a command sent to the actuator and runs, and then keep going, and then it predicts until the model is solved for this moment. And then it goes to the correct mode, and then correct the command through this time to the calculated command. So it goes from prediction mode to correction mode, and then so this is called a soft real-time approach. Yeah, because so in this approach, so the model has a longer time to be solved. So then the model can be more complicated. So that's the third option we offer. And to do hybrid simulation, so a lot of times you have a lot of challenges, and you need a lot of investment to build a structure, to build a specimen, to build fixtures, to build to come up with the compensation method. So it's very risky test also. So you want to make sure, before you make this investment, the test can be done successfully. So you need to simulate the hybrid test first. So we have a virtual testing method and different virtual testing method to simulate the hybrid test. For example, our master software could be in one kind of a analysis package, maybe could be OpenSys, and then simulating the numerical substructure. Then we use another model to simulate the test fixture, real test, and physical substructure. So then we use OpenFresco to connect them together and to do software to software hybrid simulation to simulate the hybrid test. So in this case, and we use OpenFresco to do the communication, and in here we use a super element in the master program, and we use a slave element, adapter element in the slave program. So we do software to software hybrid simulation to simulate the real test. And also we can use a calculated channel in our controller to build a complicated physical substructure model in calculated channel, and then everything is real except the physical substructure is a virtual model as well, written in a calculated channel. So this is an example, and what we did, and about 2 years ago, we did a hybrid simulation test at Ecole Polytechnique University in Montreal. So a lot of difficulties. So we created this virtual test system in using calculated channel, and so this is the code of that part of the code of that virtual system with the specimen, and then so we simulated the real test and solved a lot of problems, and so after that we went to Ecole Polytechnique and did the test successfully. So another challenge for real-time hybrid simulation is time delay, and because of a servo hydraulic system, and you send a command, and then you zoom in, and the feedback is always lacking. And this delay could be 10 milliseconds, could be 30 milliseconds, and so, but always delay. So this delay in the regular test, it doesn't matter, and who cares about 30 milliseconds? But in hybrid simulation, this delay, because it's a systematic delay, always delay, and the numerical model doesn't care about that, and it gives us command and the right way reads the feedback. So this kind of delay in analysis model will accumulate, and if the acting like a negative damping. So if your system has a relatively low damping, and then so this negative damping will cause stability issues. So you have to do a delay compensation, and so we have all kinds of delay compensation methods. So this is a self-adaptive delay compensator, adaptive feed-forward compensation method. So we use this very often, very effective. So next, I'm going to talk about the example, and so this is a real hybrid test done at Swinburne University. So it has a big building, and then to test this building, it takes a lot of money and a big shake table, and then they only test one column. And use this column property, and then updating the properties of the rest of the columns. And so in this case, they spend relatively little money, and then studied the whole structure during earthquake. So they did a comparison. They did a traditional quasi-static test, and then you see the damages, a lot of damage. And then they simulated a real earthquake, and the damage is much less. So this shows that hybrid simulation is more accurate. A traditional quasi-static test is artificial command, and sometimes is causing over-design. So next, I'm going to talk about the trend in hybrid simulation. So we see more and more tests, real-time hybrid simulation tests, coupled the shaker table, using the shaker table to do real-time hybrid simulation. For example, this tall structure with mid-level isolation, and then the traditional way is to do the hybrid test on this whole structure, and then you have to shrink down the scale a lot. And if you do the hybrid test and only test a part of the structure, rest in the analysis model, and then the test is more efficient, and you can test a larger scale of tests. And also, there's another trend is to do shaker table coupled with the loading actuator test. And again, for this example, and you have a mid-level isolation, and you have other signals, other device to connect the adjacent structure. So then you can use actuator to simulating the interaction here, and then you can simulate the interaction at this isolation surface. So then this is a shaker table coupled with the loading actuator real-time hybrid simulation. So about 3 years ago, we did a test at Tongji University, and MTS coupled teamed up with UC Berkeley and did this real-time hybrid simulation and simulating bridge, and so the foundation and foundation is in the numerical element, numerical substructure. So the inertial effect of the weight is in the substructure. So in the middle is the numerical physical substructure. Yeah. So foundation is numerical, and the weight is numerical. Middle is the physical substructure. So then you can see, so this is the physical substructure. The weight is gone in the numerical substructure, and the effect of the weight is applied by the loading actuator. And so this is a shaker table coupled with loading actuator hybrid simulation. So we used the delay compensator and very successfully executed this test. So another trend is to use a degree of freedom control to do hybrid simulation. So you can see here there are two actuators. If you can give a command only to this actuator, this does not move. It goes to an arc. And the same thing goes the other way. So UF control and controls global coordinate system. You give a S command, and then both actuators move. Ensure a pure X direction motion. You give Y, same thing. So, for example, this structure, behind up in front of you, and there is a 6 UF loading system, and it controls X, Y, Z, and rotation, displacement, so that you can control any location 6 UF accurately in force control or displacement control. So then FEA calculates the command can be easily executed through this kind of a loading device. And so there are other systems, and this is the EcoPolytechnic 6DUF loading system. You can see the difference is here. The main difference is here, the swivel. So in this system, it has a hydrostatic bearing. The friction is really low, and in EcoPolytechnic, it doesn't have that swivel. It has a regular swivel, a lot of friction if there's a lot of tension, vertical force going up. So that friction causes the force loading, and then when you do hybrid simulation, it will cause stability issue. And so we had a lot of problem with the stability issue with this system, and we need to slow down the test significant to overcome that friction problem. And even though we do so slow, and we still need to come up a friction compensation method. So we simulated a 10-second earthquake, and it took about 48 hours. So in here, you will see the hybrid simulation test will be much faster. So, and other examples of multi-axis loading device coupled with hybrid simulation. So this is a Berkeley 6DUF control system, and another 6DUF control, a 4DUF control system at Berkeley. And so another trend is, hybrid simulation method is used in other industries, like in ground vehicle. So about several years ago, 5-6 years ago, hybrid simulation technology is used in ground vehicle. So this is MTS four-corner damper system simulating the damper performance and simulating the vehicle and going through different events. The physical substructure is this damper system, and with active control. So there's okay, that's later on. And also in wind energy, and we worked with the DTU, Denmark Technical University, and tested part of the blade and analyzed the rest of the blade. And the project is ongoing, and so this is in wind energy, and also in aerospace, and at University of Bristol, they did a hybrid test, real-time hybrid simulation to simulate one damper, and the rest of the helicopter structure is modeled, and so this is a real-time hybrid simulation. Yeah. So, in summary, and real-time hybrid simulation method, could be a very efficient method, and it could be more accurate than traditional tests because the command is from analysis model, so you can simulate all kinds of dynamic events, and the test is more accurate because it gets the command from analysis model. Analysis model is simulating dynamic event. Yeah. So MTS has been in this field for quite many years, and we work with a lot of top-level universities, leaders in this area, such as UC Berkeley. We offer all kinds of methods including quasi-static hybrid simulation, real-time hybrid simulation, soft real-time hybrid simulation, delay compensation, and all kinds of methods, friction compensation. So we want to be the leader in this industry, and we want to help you guys out. Thank you. So, questions?
Testing?
Thank you. I got a few questions, if you don't mind. The first one, you said you need the CSI program, but you still need, like a regular program like MPT to run all the,
Oh, that's a good question. So CSI controls the actuator, controls the control channel. So, here. So OpenFresco sends the command to CSI. Then CSI gets the command directly sent to the control channel, sent to here. So then this control channel is occupied. So the MPT cannot get access to that channel anymore. So MPT can still run in parallel, but MPT can only collect data there. MPT cannot send the command to this channel anymore.
But CSI will run the pumps and all the hydraulics?
CSI will send the command to that channel, the actuator will move. So 793 software has to, put the hydraulic on and put a high level, low level.
Okay.
793 has to protect the specimen with the limitations, stuff like that. Yeah.
Okay. Next question. What are the inputs that CSI use? I mean, it use only the force and the displacement of the actuators, or it use on other signals like external signals like LVDT or strain gauges? I don't have that so clear.
So CSI has access to all the signals in 793 software, in the controller software. So for example, if your control channel has a displacement control, force control, acceleration control, and then you can, here, you can pick, in here, force control, displacement control, acceleration control. And so OpenFresco need feedback. And then, so CSI can provide anything, temperature, displacement, force, and whatever in certain order. So OpenFresco has a, request, has a signal order, and then CSI, got to be in that order, and all the signals can be fed to OpenFresco.
Okay, so the signal which is the control mode in the physical test should be the same signal on the analytical model, right?
Correct.
Okay. Yeah. And the last question, I'm sorry, how long it takes the example of the test that you explained first, how long it takes to run it? That
this one?
Yeah, that one.
This one. This one was done by Swinburne University, and I think they intentionally slowed down the test to measure the crack growth and that kind of things. So I think it took about 4 hours.
4 hours.
Yeah, but it definitely could do much faster than that because of the test system capability. And you will see a demo here. Probably it will take about 1 hour to simulate a 35 seconds earthquake. Yeah. So, but for this test, intentionally slowed down the test. So it went much slower than that. But for this test, because the friction problem, it had the stability issue, so they had to keep the integration step tiny. And then took a very, very long time to get this hybrid test done.
Thank you. Thank you very much.
Any other questions?
So my question is related to the simulation tool itself. So, if I were to look at the concentric cross frame that you looked at, during the testing, if the buckling, for example, is taking place in a different mode or in a different fashion than what you assume, do you have the ability to go back and modify your analysis itself?
So model updating?
Yes.
Okay.
Based on what we are learning as the new things from the testing.
Yeah, so model updating, like Shirley mentioned, so it's a advanced topic, and UC Berkeley did that, and Purdue did that, and NCRE did that. So in OpenSeas, we believe that there's Agor's special method to do that, and that's a subject we are going to work with UC Berkeley to implement that at MTS. So at this moment, we don't have that model updating capability at MTS, but maybe next year.
Any other questions for Sean? If not, Sean, thank you very much, and give you a round of applause for your work here. Thank you.